All right, so in this video, I'm going to talk about the pseudo-steady state hypothesis. So we've looked at the rate determining step method. Today we're going to look at the pseudo-steady state hypothesis. Both of these methods or strategies are ways that we can derive rate laws for reactions based on a postulated reaction mechanism. So to do this, to do either method, we need a postulate of a reaction mechanism or a hypothesis of a reaction mechanism. Sometimes that's done for us, and sometimes we have to do it on our own. The process or the procedure of developing a reaction mechanism and testing it is not simple. It's not hard to postulate a reaction mechanism, but whether that works or that works under all types of conditions, that remains to be seen. So if someone has given us a good reaction mechanism, I think it's good to use that. And if not, then we have to postulate one. But then what we can do once we have a mechanism is we can use one of these methods, either rate determining step or pseudo-steady state hypothesis, to get us to the place of having a rate law that we can use in a reactor design. So this is a key challenge. Other ways that we can do this, and it's possible that you do this in your lab class, in your unit ops lab, is to collect experimental data about a reaction, and then you can look at the reaction under different concentrations, under different temperatures, and you can use that to postulate a rate law. There's actually a chapter in the Fogler book dedicated to that. I believe it's chapter 7. We will not cover that in this class. In this class, we're going to talk about both the rate determining step and method and the pseudo-steady state hypothesis method. In these methods, what we do is we postulate a reaction mechanism. We make assumptions about the rates of certain steps and or the concentrations of certain species, and we develop a rate law based on those assumptions. When we do this, our rate law is not complete. There's going to be some parameters in there. So there's going to be rate constants. There's going to be equilibrium constants of different steps. So we would need to obtain values for those. This can be done experimentally, for example, in a similar way as this this strategy, where we would measure the rate under different conditions and use that to parameterize rate orders, as well as the activation energy or the rate constant. It can also be done computationally. Okay, so without further ado, let's talk about that. In this class, we're going to focus on the second method, where we postulate a mechanism. We make assumptions about the rates and or of certain steps and or the concentrations of different species, and then we use that to develop a simplified rate expression. A challenge to doing this is that the steps in the reaction mechanism tend to occur on different timescales. So the steps So what I mean by that is that some reactions will proceed quickly and others not so quickly. So when we construct a rate law, one thing that we can do is to group the steps in the mechanism into fast steps and slow steps. So this is what we do when we use the rate determining step method. Basically, in the rate determining step method, what we're assuming there is that there's one or two steps in the mechanism that are slow, but then all the rest of the steps in the mechanism are fast. And what that means, if all of the other steps are fast, and they're basically waiting for these one or two slow steps, what that allows us to also assume is that all of the fast steps can come into equilibrium. And when I say equilibrium, I'm not talking about the overall reaction. The overall reaction is not in equilibrium because one or two steps are slow. They're kinetically limited. But all the other steps all the other steps are able to come into equilibrium. So each individual step can come into equilibrium. This is an assumption that we can make. This is not the true equilibrium because the slow reaction steps are kinetically limited. If there's a couple steps in the mechanism that are kinetically limited, then the overall reaction itself is also kinetically limited, so it's not in equilibrium. And so these steps that are in equilibrium, we call this either a constrained or a quasi-equilibrium. What that means is that those steps are in equilibrium, but the overall reaction is not. In the rate determining step method, in that case, we assume that all the reactions except one, and it can actually be one or two, but we're basically going to pick one. So all reactions except one are assumed to be in quasi or constrained equilibrium. In fact, let's say the way that sentence is written, let's say except one or two. So all but one are in quasi equilibrium or constrained equilibrium. And then we basically pick one to be the rate determining step. So the remaining slow reactions, so we could say one of the remaining slow reactions is the rate determining step. So we're basically going to pick one of the slow reactions. We kind of have to do this based on what we know about the mechanism. And then what we're going to say is that the rate law for the reaction and also the rate of reaction is that of the rate determining step. There I'm abbreviating rate determining step with RDS. So another method for obtaining the rate expression is the pseudo-steady state hypothesis. This is abbreviated PSSH. It's also called sometimes the quasi-steady state approximation or the quasi-steady state assumption, and abbreviated QSSA. In this method, we are going to talk about, or we're going to make assumptions based on species rather than reactions. In fact, what we're going to say is that species rapidly equilibrate. So rather than some reactions rapidly equilibrating or relatively rapidly equilibrating, we're going to say that certain species rapidly equilibrate. And specifically, what we're going to say is that the net rates of generation of all the intermediate species are going to come to zero. So all the intermediate species are going to rapidly equilibrate. So this hypothesis, or the PSSH method, is a good model to use when you have species with fleeting existences. So for example, gas phase reactions that rely on collisions between gas phase molecules. Two molecules might collide and break apart to form a radical species. That radical species is going to be pretty reactive. It's not going to have a very long lifetime, and henceforth its concentration is going to rapidly equilibrate. This is a place where a pseudo-steady state hypothesis would be a good method to use. An alternative for the rate determining step method, in the rate determining step method, we often use that in catalytic reactions. So in catalytic reactions, the catalyst is going to promote the rates of several of the mechanistic steps, but inevitably it's not going to do a great job at one or two steps. So those one or two steps are going to be the bottlenecks, and they're going to control the rate of reaction. So the rate determining step method is a good strategy for getting or estimating the rate and the rate law of a catalyzed reaction. That is to say, that doesn't mean that the PSSH method can't be used for catalytic reactions. In fact, it's used quite frequently to estimate the performance of catalytic reactions. And that's because the nice thing about the pseudo-steady state hypothesis is that we're not making any assumptions about the rate determining step. So another use of the PSSH method is when we want to assess a reaction mechanism without making those assumptions. So just different reasons for using different models. Okay, so let's do an example. So this is an example of the pseudo-steady state. We're going to use the pseudo-steady state hypothesis here. So this says, given the following mechanism for the NO2 decomposition mechanism, use the PSSH to derive an expression for the net rate of generation of molecular oxygen. So this is a homogeneous gas phase reaction. It's promoted by light. So that's what we see here. That's written into the reaction. Okay, so first let's make some assumptions about these different steps. And this is a case where someone else has postulated this mechanism. So as a first pass, I'm going to just take what someone else has done. I'm going to take this mechanism as they've given it to me. So someone else has done this work, right? So postulating mechanisms, writing rate laws, it's all very challenging, right? It involves thinking about what the mechanism might be, testing it against experiments to kind of see if it's okay. So there's a lot of work involved, right? It's not a simple process. So because of that, if someone gives me a mechanism, my first pass through, I'm gonna assume that what they gave me is correct, right? I'm gonna build off of the work that someone else has done. Now, I might get to coming up with the rate law and find out that it's infeasible, and then I might have to go back and undo some assumptions and make some new assumptions. But as a first pass, I'm gonna just take what I've been given. So I was given this mechanism, I'm just going to work with it. So based on this mechanism, I'm going to make several assumptions. I'm going to assume that this step here is irreversible. That's because it's been drawn with a single-sided arrow. Now, I can't always trust the way people draw arrows. People draw arrows kind of haphazardly without thinking about it. That's why I'm going to say that this is an assumption. I'm assuming that this is a irreversible reaction. I might have to go back and check that or fix that later. If that's the case, I will do that. But for now, I'm making the assumption that that's a irreversible reaction. I'm going to assume then that the second reaction is reversible and that the remaining are irreversible. So I'm going to say my assumptions are written in red. Okay, so now I've made my assumptions about my different reactions. I want to write a statement for the rate of generation of O2. So that's what we're asked to do. So the net rate of generation of O2 is going to depend on what reactions that O2 is involved in. So we're going to say RO2, and that is going to be RO3 plus RO5. So molecular oxygen is produced in reactions 3 and 5, and that's the only reactions that it's involved in. So now what I'm going to do is I'm going to write the rate laws for these two different reactions. I'm going to assume that these are elementary reactions, so when we write, or they're elementary steps. So when I write a reaction mechanism, that's an assumption that I make. So I'm going to assume and sometimes that's true and sometimes it's not. A lot of times in reaction mechanisms, we might lump together a bunch of quasi-equilibrated steps, for example. So those wouldn't necessarily be elementary reactions, but maybe we can treat them as elementary reactions because they're a combination of a bunch of quasi-equilibrated elementary reactions. Regardless, this is an assumption I'm going to make, and maybe I have to go back and fix this later, but for now I'm going to make the assumption. Okay, so I need the rates of, here, and I wrote this incorrectly, so that should be 3 and 5. Okay, so now I'm going to go and write rate laws for reactions 3 and 5. So that's going to be K3 CNO3 CNO2 plus K5 CO CnO2. And since reactions 3 and 5 are irreversible, I only need the forward reactions. All right, so now what I must do is get rid of these terms. So those are my intermediate species, NO3 and my NO3 and my atomic oxygen. Those are intermediate species. I know that because they are not involved in the overall reaction. So my overall reaction involves nitrogen dioxide, nitric oxide, and molecular oxygen. It does not involve NO3. It does not involve O, because those are intermediate species. And an issue here is that this is a gas phase reaction. Henceforth, the concentrations of NO3 and O are going to be very hard to measure because those species are going to have somewhat fleeting existences. Okay, so take, for example, the oxygen atoms, right? Oxygen atoms in the gas phase are not going to last long. They're going to want to combine with things because they are very unstable. So therefore, it's hard to measure the concentration of those species. Henceforth, I can't have a rate law that has the concentration of oxygen atoms in it because I don't ever know what that is, right? So I need to come up with an expression for CO. And also, I'm going to come up with an expression for CnO3 for pretty much the same reason. So my intermediate species are NO3 and O, and I know this because they are not present in the main reaction. So what I'm going to do now is I'm going to apply the pseudo-steady state hypothesis, which says, okay, these are my two intermediate species, and that means that the net rate of generation of these species must be equal to 0. So what are the net rates of generation of O and NO3? So our RO is equal to 0 and our NO3 is equal to 0. And I can also use my assumptions that I've made about the mechanism to fill those in. So the rate of formation of atomic oxygen is going to be, it's going to have contributions from reaction 1, reaction 2, which reaction 2 is reversible, and reaction 5. And then NO3 is going to have contributions from reaction 2, reaction 3, and reaction 4. So now what we want to do, we have essentially 2 equations and 2 unknowns. My unknowns are CO and CnO3, and I want to solve for these. I want to solve for those expressions. And so that I want to do that so that I can eliminate them from the expression for RO2. So let's do that. And let me preface this with the fact that there are many ways to work through this algebra. So I'm going to show you one way. It may not be the best way. In fact, it's probably not the best way because I used to be really good at working through algebra, but I just don't do it anymore. So maybe it's not the best way, but there's many ways to do this. So I'm going to go through and rewrite my 2 expressions. One thing I'm going to do is I'm going to sum these 2, and that's because if I do that, I get rid of these this expressions related to reaction 2. So that gives me something a little bit simpler to work with. Oops. so now I can go ahead and write that out. Okay. Now what I'm going to do is add this expression, so this one that results, to my expression for RO2. The reason I'm going to do that is because then I get rid of these two. So I'm eliminating. If I do that, then I would say, and I could do that because this is equal to 0, right? So I can add, so this expression is equal to 0, so I can add 0 to anything. Essentially, I'm adding 0, and that's going to give me, and I should say 0 here, where by 0 I mean that 0. And actually, it is that, but I guess more, I'm adding that 0. When I do that, I get just R1 minus R4, which is equal to K1CNO2 minus K4CNO3 CNO. Okay, so now I can basically solve this for either CO or CNO3. And actually, what I'm going to do here, okay, no, I'm going to leave this the same. So I'm going to say this is now my expression. This is an alternative expression for RO2. And so what I've done here is kind of simplify down into having this one term here that I need to worry about. What I'm going to do now is I'm going to use my expression for RO to write CO as a function of CNO3. So I have 0 equals K1 CNO2 minus K2F CNO2 CO K2R CNO3. Okay, so I can start to pull out terms here. Okay. And then if I make one further simplification, I can say CO is equal to K1 this is writing this very sloppily. Let me redo it. Okay, so now I have CO as a function of CNO3. So we'll say sub this expression into RNO3. So then RNO3 equals 0 equals K2F And then I can use this to solve for CNO3. Okay, and then finally, there I should have no instances of, CO in there. So now I can finally sub into my alternate expression for RO2. So if I do that, then I have RO2 is going to be equal to K1C NO2 minus a very large term here, so I'm going to okay, and then up here I would have K1, K2, K4, CNO2, CNO. All right. One thing I can do now, so I have all these terms where I have constants that are multiplied and added together. In reality, if I was going to test this mechanism, I can't get details to that level. I can't, for example, distinguish out of this group of constants, I can't distinguish what is K1, what is K2, and what is K4. All I can distinguish is that I have like one constant there. And to be honest, I might not even be able to distinguish that much because I have a lot of constants here. So another way I can do this is to simplify. So I can say, for example, RO2 is equal to K1 CNO2 minus, we could say, let me do this. I don't need that large of a, let's say K prime CNO2 CNO divided by K prime prime CNO2 plus K prime 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 CNO plus K prime 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 prime, or something like this. So this gives me a simplified mechanism where I don't need to worry about each individual constant. I only need to worry about groups of constants. So here is a simplified mechanism solved algebraically using the pseudo-steady state hypothesis, and this right here is then the rate law that results.